Let's start recording, and everything is being shared. Okay, cool. Right. So we're going to talk about two things today. We're going to talk about practical cases of AI and something very close to you, like the transport services inside Oslo and Beacon Commune, which everyone can relate to. And then the second half will be based on generative AI. So we will learn what is generative AI, what is large language models, and I'll tell you about the architecture and the the, the theory behind generative AI. We will not get time to cover. We will not get time to cover prompt engineering today. Okay, how do you do this? What is wrong? Okay. All right. I don't have to cover this part, but let's talk about the scale of the things happening inside Router. So Router is a transport company, and Norway we know is very small, right? It's a population of 5 million inhabitants only. But most of those inhabitants live in densely populated areas, like you have Oslo, you have Bergen, Stavanger, and so on. The reason why Router company like Router is so important is because at any given day they have around around 1 million people that transport almost every day on a daily basis. So that's a lot of people being transported. So what I'm going to do is I'm going to cover like different projects done by Router in the last 3 years. We have done around 18 different projects, and almost 16 of them are already in production. So you can actually, if a project goes into production, that actually means that there are actual users of this AI project. You have exported it in some way or the other to people who are using it. And then we have also managed to build an AI department, which is very attractive. So we get a lot of applicants every year. So the last time we hired some people into the department, we had almost 250 CVs coming in. So it's and we also have a quantum computing area. Okay, so the first project I'm going to talk about is fleet management. Have you seen these kind of buses going around in Oslo and Beacon? Yeah, okay, some of you have, others don't. So these are like green, these are small buses, these are not big ones, these are green ones and the pink ones. Now, this transport is designed for, this is a distilling transport. What it means is it's like an order transport, it's like an Uber. But when you order an Uber or a cab comes to you, picks you and takes you to a specific place. In distilling transport, it's the same concept that you have an app and you order the bus, but a small bus will come to you, pick you up, and then it will pick someone else. And if the same route, then it will pick all the people and take it to that specific destination. This service is being tested only for older people. Now, when I say old, it's like the old ratio in Norway is pretty high. So these are people who are 80 or 90 years older. And then children who want to go to school or who are going to their after school activities, which is very common inside Norway. So the problem we had was that when it was normal time, everything was fine. But when it was a rush time or a peak time, the drivers were just driving around. And sorry, the opposite. When it was the rush time, everything was fine because the drivers knew where the orders were coming from. They went from one place to the other. But when it was a normal time, drivers could go and do whatever they wanted to do. They could go and talk to their friends. They could talk to a coffee shop. They could go to a petrol station. And that meant that if an order came from a specific place, which was on the east side and the driver was on the west side, the driver had to go, and it meant like wastage of time. So what we did was we knew where the orders, the service had been running for a few years. So we had information on the historical data, and we made an algorithm which kind of predicted where the next order will come from. And you can easily do that because you already know where orders have been coming from. So what we did was we picked up postal code information. Now, if you take a look at the right-hand side of the image, the right-hand side shows you the actual demand. Like any given day, this is the kind of demand which comes in. You have demand coming in, so everything is divided on a postal code location. And we took that information and we made an algorithm. So the left-hand side is the demand predicted by the algorithm. So you can see some areas are a bit off. You have different kind of demand close to this area, not that area. In this area, you have a different kind of demand. You have some abnormalities in this area and those areas. And when we measured how much predictability we get, the algorithm was giving us like 70% correct predictions and 30% wrong. But this is a kind of an algorithm which is okay to have 30% wrong predictions because it's not going to impact anyone's life. We're not working with health. We're not working with military services or security services or so on. So the benefit of using this was that we are now using this data and algorithm to tell the drivers that instead of driving around, go and stand at a specific zip code for the next half an hour because we think an order will come from this area. And this has resulted us in saving fuel cost and making our customers happy because they don't have to wait for like a long period of time. And also the sustainability part, because now the buses are not driving around, so you don't have a negative impact on the environment. The second project, how many of you have experienced ticket controllers inside Oslo? Yeah? Anyone who has not? Oh, okay. It's a cool experience, right? So ticket control is a very sensitive topic for Ruther because whatever we do, no matter how good or bad we do, will always end up in the media. And this is something which kind of negatively impacts many people in a way, like even if you are a person who buys a ticket and someday for some reason if you forgot to buy a ticket or something happened and you forgot to pass home or one thing or the other, it's not a pleasant experience to be actually have to talk to a person who would give you a fine. But unfortunately, we live in a world that this has to happen. So before I tell you how we use AI in ticket control, it's important for me to say like the concept behind ticket control and why we have it. Ruther is a company which is a state company. So half of the funding comes from the state and the remaining half comes from the sale of a ticket. But we are owned by the state. So the difference between a private company and a state company is that a state company does not make money from the people. The whole purpose of a state company is to provide services for the people. So if a state company has a service like ticket control, it's not to make more money. It's actually to create an effect that the society will actually convert into buying more tickets. And that's the difference between that. If you look at ticket control process in Ruther today, it's not something we make money on. We lose money on this process, on this project every year. And yeah, so what we started looking into the process was like, is there a way we can optimize the billet control process? So the billet control process, the reason why it loses money, one of the reasons why it loses money is because it's a very manual process. So you don't have one person or one algorithm making a decision. You have people in Ruther who make a decision. You have 10 or 5 different people who make a decision, like we have to control this stop, or that stop. And then you have many other people in the second company, the outsource company, who make a decision. And these people talk together. When you have so many people making these kind of decisions, when you put people in a decision-making process, somewhere down the line, things can go wrong. And then you have a lot of time being spent on the decision-making process. So we looked into that aspect, like how can we optimize this process? How can we take away the decision-making process away from people and move it to the algorithm? Then the other thing we came across was a lot of people were talking about why is my area being controlled more than the others? Why do I see people controllers coming in this area for some reason? So when we started working with billet control, our first starting point was we wanted to predict the same with distilling transport. We wanted to predict areas where sneak would happen. And the way we could do that was looking at historical data, because we already have data coming in from ticket controllers. Yeah. Yeah, okay. So, but, okay, I'm gonna black out the screen and I'm gonna ask a question. So we had data from before. We knew where controls were happening. We knew where people were the stops where people were sneaking more. And we were like, okay, now we need to use this data and create an algorithm which can also do the same kind of predictions. So we replaced the human part. But is there a problem with this kind of flow? Do you see a problem with what we did? Yeah?
Bias.
What kind of bias?
The algorithm would take it does its job. It highlights the parts where the sneaks have more of. Right?
Mm. Okay. Any?
Sure, I don't really see the problem.
All right. Yeah, okay. Anyone else? Sorry.
I think you try to say survivorship bias.
And what is that? Could you elaborate?
Bias where you pick and you have a set of data, and let's say it's called subject bias typically because you see the example of the damaged aircraft returning, you see where it's damaged, and you're trying to figure out how to prevent the planes that didn't make it home from not making it home. You can't look at the area where the planes that returned took the damage and protect them. You got to look at where the planes that are returning that aren't that are returning where they aren't damaged, because it's probably obvious to think that these aircraft that are not returning because they're taking damage to critical areas that are not sufficiently protected.
I'm not
And
following.
the same.
I'm not following. I'm sorry.
I'll just find you the picture of it because it's like a really cool example.
Yeah.
If you shoot the plane in the engine,
Yeah.
it won't survive. But if you shoot the plane in the
Okay, I think I've seen this. Yeah, okay, right. Now I follow.
You don't armor the places that the red dots are. You
I
armor
see.
the places that aren't.
I remember
the same
that.
Kind of applies here. If you're having data that shows, then I think that's what he's trying to say.
Yes.
If you're having data that shows that there's a lot of people speaking on, let's say, Grönland, and I don't know, just take another Holman column, whatever, right? Then chances are it's just going to keep predicting that.
Good point.
And this other thing is the data you've taken in is not evenly distributed. You don't have it, or at least not compensated for that.
Yeah.
Let's say you have a lot more traffic on some Coast West National,
Yes.
so therefore you're more likely to be controlling these areas. Then you're not really getting the true data evenly distributed across all areas. And if you're not compensating for that, you're just going to end up with saying that you have more people speaking in these areas.
Correct.
As a correlation to there being more people there to begin with.
Yes. Very true. So now the point you have highlighted is the data part. You're looking at the data aspect, and you're thinking like, okay, you're not covered all the data areas. And this is the same problem as the bias when it comes to the impact it will have on people's life. Like people can argue by saying like one side can say like we don't think there's any bias in data at all. But the other side, people who live in the society can say like there is bias in the data because I know in my stock there are more controls being happening as compared to the other side of the stop, for example. And then you have this conversation happening. This example is very similar to Amazon creating a recruitment algorithm, which was a very sexist algorithm because the data they used was highly dominated by male applicants as compared to female applicants. Now, Amazon did everything right. The programmers were not racist. The company was not racist. The programmers were not sexist. The company was not sexist. However, they used a data set which was not truly representative of the population. And when they gave the decision-making process from people to the algorithm, it created problems for their recruitment process, and they had to shut it down. We looked, yeah.
Just is the problem fixed by just updating the algorithm?
No, that problem should be fixed by looking at the data sets. So when you are using an irregular data set, then you're telling the algorithm like there will always be a certain kind of population which should always be higher representative than the other one. So the algorithm will always learn from the data provider. In this case, we have the same problem. You are creating a ticket control process based on historical trends of where sneaks will be happening, and you use that data to train a new algorithm, which is doing the same thing. So we knew this was a problem even before we started working with it. And what we did was we decided that we cannot rely on historical data at all. So we created an act of randomness inside the data. So we told the algorithm all stops have equal weights, but now look at how many people are flowing through each stop instead of looking at what the ticket controllers gave you from the last time. And when we did that, we then had an equal representation of predictions coming out from each stop. This thing is currently live now. So most of the ticket control processes happening in IndraV, they come from this AI recommendation algorithm, which is happening. This is a tool we use. So sorry, I'll come back. This is a tool we use. So this is the kind of predictions. Okay, this is a very bad way of hiding sensitive information. I try to hide it, but you can still see it. But this is the kind of information we hand like every day to ticket controllers. Every day the algorithm makes a prediction and the predictions are sent over ticket controllers. They get these predictions and then they go to those stops. So our plan is to expand the zone from IndraV, go to the wider areas of Oslo and Viken and try it out. Now, IndraV is easy. Downtown Oslo is easy. And because it's a lot of people moving in that area, right? When you go to the east side, the west side, the north or the south, that becomes a bit more challenging because you don't have, people are living spread out. So we're testing it and we're seeing how things actually work out with that one. Sorry.
Yeah, are you limiting the, for example, I can't see that it would be efficient to controls in a rush hour.
Hmm.
Yeah, when the bus is like filled up with people. Are you kind of limiting that solution? Like if there's like more than a certain amount of people who say no,
We're not using that.
like I've never actually seen both when the train or the bus is like filled up.
They're probably happening. So it's not like the rush hour or something. But I'm not really sure of the answer here. I don't know. Sorry. Okay. Since you live in the society, you probably have seen these kind of things coming up in the media. And that's a problem. Like you, as a company who provides these kind of services, it's a problem for us to be exposed to these kind of information. And we live in a society, right? So we have our friends calling us, our spouses telling us like, something is wrong. I get a call from every few days from my wife. She's yelling at me like, why was the bus late? I'm like, I can't do anything about it. But we live in the society. We have direct impact for the consequences of things happening with this service. So one of the projects we worked with was to see like, how can we stop this from happening? This is a bad thing for the company. This is a bad thing for the society. We need to stop this from happening. We need to identify this by using AI. So the most easiest thing we could do was to look at what our customers were talking about us, and that is called that's just textual data. So what we did was we wanted to take a look at how angry our customers were. Now, if you are a user of router services and you send a complaint to us, chances are you probably have a problem which wasn't fixed. You're angry. But within that scale, there we wanted to see how, if you were extremely angry or you were like somewhat angry. So in this graph in front of you, every dot is a complaint. So there are like 600,000 complaints on this image, and this all of these complaints based in Norwegian and Swedish, they are we fed them to a sentiment analysis algorithm. And the way we trained the algorithm was that we downloaded a lot of swear words in Norwegian and Swedish, and we told the algorithm like, these are swear words. And then we also downloaded a lot of Yelp reviews and Google reviews, and we told the algorithm like, okay, now you know what swear words are. Now you know how people are angry or how people are sad or happy when they talk about different things. Now look at our data set and tell us people are angry or happy. So then the green color are complaints where people are, okay, everyone is angry, but within that scale, you want to see how less angry or extremely angry you are. So green are less angry, yellow are more angry, red are more angry, and then all the way to the red are people who are extremely angry, and they're using threats and they're using curse words and so on. Then what we did was we used this information and we mapped it out in the map of Oslo and Viken. We kind of knew where the complaints were coming from, and we were like, okay, we need to see what were the more problematic areas. And then we went forward and we made a tool around it. So what the tool does right now is that we now have a way to select on a specific bus. And if you select a bus, for example, 100, we can take a look at a timeline of the bus, where the bus started. For example, the bus started from somewhere up from Lillestrøm area and went all the way down to Oslo bus terminal. And during that journey, you can see like in the start, there were complaints, but okay, these were people who were, not that angry, but all the way down to Arnabu, there was huge amounts of issues, so we had to investigate that. So this gave us more insights into what was happening than before. The next thing which kind of AI helped us a lot was to find trends in the data. Now we as humans, when we look at different kind of data sets, it's physically impossible to look at a data which has a 1 million entries. We can look at data which is like 10, 20,000, 100,000, but when it goes beyond, we can't find trend in the data. Now AI kind of helps us over here. Remember the clustering technique we spoke about? And we were like, I think I've already showed you this. So this is the clustering we did. And we were able to group various conversations together based. This is not us, this is the algorithm who is grouping the conversations together based on the conversation people are having. And the algorithm finds the trend on its own. The next thing we did was we kind of knew what people were complaining about, and we were thinking like, can we do anything more with this information? And we realized that a lot of time was spent by the customer service in answering repetitive tasks. Like people were asking a lot, where's my bus? And we're like, instead of every customer going in and answering to that question, can't we make a bot which can reply to this question and tell them like where the bus is? So we started looking into that, and we wanted the algorithm to predict if what the person was asking for. So these were questions which were coming in from the users, and when we ran it through a prediction algorithm, the algorithm was able to correctly identify if the person was talking about the bus which was delayed or the bus which was canceled. But that the thing with AI is it's never going to do anything 100%. So there were also instances where the predictions came wrong. So this is an example of a prediction which came wrong. And when we investigated, like, why is it giving us wrong predictions? We as humans can understand that, okay, the one highlighted in red, that the bus didn't even start at all. But the algorithm got confused and it said like it was delayed. And then we investigated further and we realized that the person was talking about 2 or 3 different issues, which confused the algorithm. And the algorithm kind of focused only on one of the issues and said like it was delayed. This is very interesting. So here is something, you made an algorithm, which is a very good algorithm. You're not making a model on its own. You're reusing an existing model, but then you realize that the model, you have given a lot of data to train the model, but the model can only understand one context in the problem. When it went to 2 or 3 contexts, the model couldn't understand it. The way we fixed it is that we told the model, like, if anyone is saying complaining with more than 200 characters, you should not handle it, read out it to a human, and the human can actually take a look at that one. So this was like a workaround for how you wanted to fix it. This is in production today. So if you send a question, this is the kind of response you will get. The focus was time, so that if you're standing on a bus stop and you're asking for information about the buses, you will immediately get an answer instead of getting annoyed. Kind of wrong thing to say here, because this is not seen like AI is going to replace jobs, but over the last 2 years, this has saved us a lot of hours, like manual hours where we would spend a lot of time. Okay. The other project is capacity prediction. Like this is something you probably see. Since we already know how many people are traveling at any given time, we could easily predict how many will travel in the future. So what we know right now is that in future, for the next hour, half an hour, days, and up to 3 days, we know how many people will be traveling on every single line. How do we use this information? So we made an algorithm which does this. And if you go to Router app today, this information, like how much capacity will be on the bus, this comes from the AI algorithm, which predicts in the future how much capacity will be. Now, it's extremely important for people who are on a wheelchair, people who are carrying suitcases, people who have like a trolley or have a child. Yeah, if you're planning your travel. So one way we use this is this way. The other way we use this information is that our operations department uses this a lot to actually plan how many buses should be sent on a specific like from 7 to 9, the rush hour of peak hours. So this actually helps in making the city more sustainable, because now we're not sending buses all the time. We know exactly how many buses should be sent at any given time. Then, okay, explainable AI. Now, explainable AI is something we did not cover in our class at all. Perhaps we should have had, but okay, I'll just give you a brief overview. One of the directives or legalities which is coming in is that if you make an AI algorithm, you should be able to explain what the algorithm does. And that's the explainable AI part. So then it's also there's also a division of what kind of algorithm you are making. If you're making algorithms which are just transport algorithms, okay, it's perhaps not needed. But if you're working in health sector, if you're working in with personal data, then you need to be able to explain the algorithms you have made. So that's the explainable AI part. Many people say that AI is a black box, and it's very hard for you to explain what's happening inside that black box. But there are many researchers and professors who don't agree with that part, because what they say is that if you know what's going on in your data, if you know what kind of model you are using, you should be able to explain how you reached a specific prediction. And that's the explainable AI part. So by this time, we had done a lot of AI algorithms inside Router, and we were like, okay, we need to be able to explain what we have achieved. So what we did was we made algorithms, non-AI algorithms, which were monitoring or auditing our AI algorithms. And the way these work are like this. So you have a simple, these are predictions coming in from at any given time, at any given day, for all the buses at every single time. So what we did was we were just monitoring how the algorithm was predicting at any given time. And we knew from historical information, like let's assume the algorithm always had a prediction of 70%. Now, our algorithm, which is a very simple algorithm, is going to monitor that this algorithm should never go up or down 70%. If it goes up or down, there should be an alarm and someone should investigate why is it predicting more or lower, because the data is not changing, the model is not changing. We should always expect the prediction to be 70% because we have tested it and we have approved it. So that's the audit part. That's the controlling part. You have to monitor the algorithm. And then comes the explainability part. So then what we did was we made tools which were able to tell us how our data was changing over time and if it was changing at all. So that's how explainable AI works. So this is a very quick explanation of explainable AI. There are many frameworks to implement it. So this is one of the frameworks which we use. All right. The other project we did was to also to analyze how customers behave. And yeah, people complain using our complaint forms. But another way people complain is through social media. So people go to Facebook, Twitter, and LinkedIn, and they express their frustrations if something isn't right, or they also give some positive feedback if they're happy with the service. And we just wanted to, so what we did was we started collecting data from social media, and we did exactly what we did with our customer complaints. We wanted to see what was good, which was all right, and which was bad with our service, and we pumped the data back into the same reports we had from before. The other project we did was quantum computing. How many of you know quantum computing? Okay. All right. It's a relatively new field, so I'm just going to give a quick overview of what quantum computing is. So the way I'm going to differentiate how normal computing works and how quantum computing works. So the way normal computing works is that the whole architecture, the whole system is based on 0 and 1. Like it's either this thing happening or that thing happening. It's either true or false, 0 and 1, and so on. The whole thing is based on true or false, 0 and 1. That also means that if you want something to happen, something to take place, you have to wait for one thing to happen for the other thing to happen. Like, let's take the example of flipping a coin. If you're flipping a coin in this kind of computing environment, you have to wait for head to happen. You have to wait for head to happen until tail can happen, or head can happen again. Head and tail cannot happen at the same time because that's how 0 and 1, the whole philosophy is based. Now, quantum computing comes up with the promise by saying, like, when you flip a coin, the maximum probabilities of flipping a coin is 6, right? Yeah. And what quantum computing says is that instead of waiting for head to happen and then tail to happen, everything, head will happen at the same time, tail will happen at the same time, head will happen again at the same time. So everything will be happening at the same time, at the same instant, and you can go in and pick whatever result you want. Now, this is extremely different from how we work with normal computing today. In normal computing, we have to wait for 0 to happen to 1 to happen. But if you have 0 and 1 happening at the same time, then it gives you an immense power of the speed. This is something which is not possible in today's computing at all. And if you're flipping a coin, you have to wait for 6, let's assume you have to wait for 6 seconds in normal computing for all probabilities to happen. In quantum computing, everything is happening at the same instant. So 0 seconds, everything will happen. And you pick whatever result you need. This thing gives us extreme power and extreme speed. And that's why people are so excited about quantum computing, because this is something which is truly revolutionary for us. However, not everything can be solved by quantum computing. For example, there are 4 specific use cases which work very well for quantum computing. And you have quantum simulation, huge prime factoring, cryptography, like people talk about breaking the security for cryptocurrencies. That's something which quantum computing can do very well. But then cryptocurrencies are also based on a security protocol, SHA-256. Everything we do on internet, like our emails, our bank accounts, checking all of that is based on that protocol. So if someone is able to break that protocol using quantum computing, we have a huge problem, because then everything is going down. And then optimization. So if you have optimization problems, quantum computing is very relevant for you. Now, since we work in a transport company, we had tons of optimization problems. We want to optimize our ticket controllers. We want to optimize our transports. We want to optimize the way people find their journey from one place to the other. So that's why we started looking into quantum computing. So we did 2 projects with quantum computing. The first project we did was with capacity prediction. We tried to predict the capacity using quantum computing. And what we did was we already had an algorithm which was written using machine learning. So we rewrote the whole algorithm using quantum computing again. And what we found was that we found it was very cheaper to work with quantum computing, like server cost wise. We started working with the cloud, and it was extremely cheap. When it came to the prediction, we found that quantum computing was slightly better than our previous information. It was faster to work with quantum computing. It was extremely difficult to work with quantum computing because it's a new field, right? And when you have a new field coming in, you don't have a lot of information available and a lot of guides available. That was a problem. But we also found out that quantum computing was extremely environment friendly. And when it's extremely environment friendly, you don't have to, like one diagram I didn't show you is the power of quantum computer. Like quantum computer, the way it works, we work with bits and bytes, and we think about CPU and RAM, all these kind of things. The way quantum computer works is like, the only thing they use is qubit, and a qubit, it defines the power of a quantum computer. And a quantum computer can have 2 qubits, 4 qubits, 20 qubits, 64 qubits, and so on. Now 64 is obviously better than 2, and so on. But the power used by a 2-qubit quantum computer is the same used by a 500 qubit. So you're getting a lot of power for the same amount of electricity consumption. That's why quantum computing is more environmentally stable. The second project we did with quantum computers was using ticket controllers. Now we wanted to optimize the route for ticket controllers. We wanted to let them know, like, go to this stop and do sneak over here and go there, there. That was a route optimization problem. And we used quantum computing for that optimization. And we found out that it was much, much better than using traditional machine learning. This project, we just did it now, and we are now evaluating if we should put this into production or not. The last project I'm going to talk about is Router GPT. This is an LLM which we created, but I think we should take a break because I think I should combine this with the generative AI and LLM slides. So first we're going to talk about generative AI, and then I'm going to talk about Router GPT so you get an idea on the theory and the practical parts as well. All right, so let's meet in 9:30. All right. I hope everyone on Zoom can hear me. I'm assuming everyone can hear me. So, all right, thank you. All right, everyone, let's get back to the class. Let's do it. Okay. Now we're going to talk about generative AI and LLMs. So let's see. I'm assuming most of you know about the concept of generative AI or large language models, or if not, you probably have used generative AI in one way or the other. For example, you might have used some sort of image generation program, and an example could be as simple as this. Why is there so much light here? Yeah, much better. So you might have used some sort of image generation program. DALL-E is very famous, like Midjourney is also very famous, but there are others which are coming up. You might have used ChatGPT. How many of you have not used ChatGPT? With a show of hands. It's okay if you have not used ChatGPT, but okay, most of you have. Good. Or bad. I mean, I'm not going to judge. Someone said they have not. Yeah, okay. Then another thing with generative AIs, which is becoming very famous, is the code generation part. I guess most of you might not have used the code generation part. You should try it out. It's actually very useful for your various debugging of your code, try to understand what kind of error it is, or just generating a script if you would like to do that. So generative AI is actually becoming very famous. It's taking over, and it has shaped our lives so much in the last 6 months to 9 months that it kind of has taken the whole AI industry, not even the AI industry, the whole world by storm, and it has changed the way we interact or we look at AI very differently. But generative AI is not a new concept. It's not something which came 6 to 9 months ago. Something which came from 6 to 9 months ago was ChatGPT. And ChatGPT was something which was introduced, and everyone started using ChatGPT. And then Midjourney came, and DALL-E. DALL-E was even there even before that. So why did everyone started become so crazy about generative AI? So today we're going to discuss what generative AI is, what's the theory behind it, when did it actually start, what kind of algorithms were being working on before ChatGPT came in. I think the only thing why uh, this whole field became so important or so obvious was that when we had certain models which were so powerful, it enabled us to use them in an easy way through ChatGPT. And that's what OpenAI did. Like there were a lot of different companies working with different kind of generative AI models out there. Google was working with it. OpenAI was working with it. Even Apple was doing some sort of generative AI. But OpenAI made them available through their chatbot. And as soon as it became available, people went crazy. And then it changed the whole landscape. It changed the way we look at AI, or it changed the way even executives look at AI today and talk about it. So what really is, so let's talk about the basics. What is generative AI? So generative AI is a branch of artificial intelligence which is focused on generating content, just content. And when we talk about content, content can anything be, it could be a text, image, audio, or any kind of media. Now, a content is something which is originally created by humans, and then you give that information to an AI, and AI says like, okay, now I think I can generate it again in my own way. And that's the same way as generating an image or text or something like that. So that's the whole definition of generative AI. When you talk to someone and they ask about generative AI, this is what they're talking about, something which can generate content for you. So generative AI is not a field on its own. This is actually a field of machine learning. There are multiple models running in the bottom of how generative AI works. And yeah, the way this works is like it looks at, it tries to, it takes a look at huge amounts of data, massive amounts of data sets, and then it tries to find patterns to those data sets and then create something which is outside. The same thing as machine learning works. You have a huge amount of data set. It tries to look through the patterns in those data set and then does a prediction. Generative AI works the same way. Now you are increasing the size of data sets by huge amounts, and you're trying to find patterns through those data sets. Yeah. We need to look at how generative AI models were made. So before the whole generative AI thing started, we have something called a GAN. Now, a GAN model is a generative adversarial network. The way this works is that it's based on a neural network technology. And the way it works is that there are two neural nets which are working against each other. One produces an output and the other neural net tries to improve that output by working against the output made by the first one. If I try to explain it in easy words, you can look at two agents, two AI agents who are trying to compete with each other. And one of the agents is creating an output and the other agent says like, okay, I think this output is wrong, improve it. And it improves it again, and so on and so on. So this improvement process will go on until it reaches a final point. So GAN worked on that philosophy, and GAN was widely accepted and was widely used. This was the first kind of generative AI because it was actually two AI agents working closely with each other and trying to improve processes or content. And they were creating data which was very realistic. It was fake, but they're trying to create something which could exist in reality. And the way, yeah, okay, so GAN models were used in all kinds of data types. They were used in images, music, and text. They were used everywhere. This is an example of a tool which was made using GAN. And the way you can see this is that they have uploaded simple images to that tool. And just by using GAN model itself, they are manipulating the image and moving the image around. This kind of manipulation was extremely hard, even by us, by using Adobe Photoshop or something. But like you can see how easy it is to manipulate an object or the video itself by using just GAN. We're not using ChatGPT, we're not using DALL-E, we're not using anything else. We're just telling the GAN model, like this is an original image, but we want the new one to be like that. And then it changes it, and it changes and so on. This is used in Adobe Photoshop as well. They're also using a lot of GAN behind it. So GAN was extremely popular and was the only thing used for generative AI. But then there was continuous improvements happening in generative AI. So the second thing which happened in generative AI was another kind of models, which were recurrent neural nets and long short-term memory ones. Now, the thing about these two models is they were focused only on the language part, and they were trying to predict what the next word will come in. But the way these models were working, that they were only focused on the sequential prediction part. The sequential prediction part, because language is hard to work with. There are multiple ways of describing one single problem. And there's the same way can be described. I'm talking in English, you're talking in English. What I say in English can be described in a different way when you say it, and a different way a third person would say it. And when you give that power to the model, it becomes extremely hard for a model for any language to be able to understand, okay, if I'm trying to say I'm going to drink coffee, as simple as that. And I only say like I am going to, and you give that information to the model and ask it to predict, it will be extremely hard for the model to predict without knowing the full context of what I want to do, where I am standing, and so forth. So when you think about sequential prediction, these models had a hard time doing what kind of sequence prediction. But when we went to large language models, it became easier for those models to do the prediction. I'll talk about why. These kind of models, it was hard for these kind of models to do the prediction because they were using a lot of computational power and they didn't have enough context to be able to predict what the next word will come in. But then in 2017, some people at Google came up with a research proposal, and they wrote a paper called "Attention is All You Need." And that paper works on the attention mechanism, which actually says that we need to focus on the attention part, on something happening before and something which will happen afterwards. And when you focus on that attention part, then you also focus on the context of what's happening around it. And then you try to make a prediction on what's going to come afterwards. And when you talk to a large language model like Chat GPT, it knows what you're talking about because you give it the context needed for that conversation. So this paper was based on that theory. And when they started implementing it, they made large language models like GPT and BERT. GPT was the one made by OpenAI, and BERT was made by Google. Another way of explaining this is that, the way you want to identify attention in any sentence would be like this. A sequential way, if you use like the older algorithms, the way they will try to find associations between sentences is by going forward or by going backwards. And that's the way they will identify relationship between in that sentence. The sentence is simple as the teacher taught the student with the book, right? Now, if we use a transformer model, which is using an attention mechanism to train it, then things will be more different. The way this will work is this model will go through each word and try to find a relationship with every other word in that sentence. So instead of having like a sequential approach, like, okay, just go forward or backward, which what the oral models were working with, now we're going through word by word, every word, and we're trying to find which word has a best or a closest relationship with one another. Now we're trying to focus on the attention part. That's the key here. We're not on the attention part yet, but now we are on the attention part. Because once we were able to find relationship between different words, we were then able to find different kind of attention. What is the most closely related word and which word is the least related with each other? So the ones marked in yellow are the ones closely related and they have a higher attention to each other. So that also means that if the word book is associated very strongly with the word teacher, student, and so on. Student is strongly associated with the book and teacher is strongly associated with the book. Now, when you make these kind of connections, these kind of attention mechanisms on a structure, then the model will be able to predict what kind of question you're asking it, and it will be able to give that response to you. Right now, the model only understands this sentence. But think about billions of these sentences. Think about trillions of these sentences. And if you find attention mechanism in all trillions of those sentences, then you have a model which can effectively communicate with you, which understands what you're trying to say. And that's what ChatGPT is. That's what the BERT model is, and so on and so on. So what we have done is given the power to the model to understand different association between different things in Norwegian language, in English language, in different languages around the world. And then the model can understand, like if we talk about going to a cafe, then we'll probably go to a cafe to sit down, to calm down, to drink coffee, to eat a sandwich, and so on. The model will understand because the model has been trained about different scenarios and attention mechanisms around the cafe. Yeah.
So it doesn't need to know the word or the loading of words. So it needs to know the connection to the other words.
Correct.
So that's the most used word in the English language that it has a lot of connections. So
Correct.
it would be in the center of the like connection between. So
Yeah.
from that, you can get some decent text.
Correct. For example, to further expand that, if you want to do math with a large language model or something, it won't be able to do a proper math for you because it will try to predict what will happen next. So it doesn't have to understand the meaning of a word. It just has to understand the relationship between the words. And if it has understood that 2 + 2 relationship comes to 4, it will show you 4. But if it has understood that a 2 + 2 relationship is equals to 5, it will show you 5. So it can hallucinate. This is called hallucination. This is called something which the model is just making things up because it has understood in a way this thing belongs together in that way.
So if you train it using only the Morse code, it would work just as well. Or
Yeah.
use like whales or something.
Correct. I think you were talking about this excellent example of a chess game, right?
Yeah.
Could you share this with the class?
A funny YouTube video. It's like a 3 or 4 minute YouTube video or something. We'll try to find some.
So I don't think we'll be able to show the YouTube video just because we have people on Zoom. But is it okay if I just rephrase what you told me? Yeah. So we were talking about how it's impossible for large language models to play chess. And you told me that the model actually generates different moves on what it has learned, and the moves can be completely wrong, but it has learned those associations by looking at historical information. But if you give the context, and I'll tell you what the context is. If you tell the model like, okay, this is how chess is played, and this is how it has been played before, then the model will actually give you information in a much better way because now it knows different kind of associations, different kind of attention span. By the way, it would be nice if you can send the link afterwards. I'll share with the class.
Yeah.
Thanks. Okay, so that was the attention mechanism. That was the transformer. That was the transformer. Where am I? Yeah, that was the transformer model. Transformer model is an architecture. That's the solution they came up with. This is the architecture we should follow. And then someone came up with the solution of a large language model. So large language model was the implementation of the transformer architecture. So what really are large language models? Large language models are huge amount of large language, like models which are trained on huge amounts of data sets, and they focus on the generative AI. They want to generate content, but since it's called a language model, it will only work on language. It will not work on media. It will not work on audio. It will not work on that. It's a large language model. A large media model would be something else. But if you're talking about large AI models, it's everything. It's media, it's images, it's text, and so forth. But a large language model, because many people confuse this term. Now, examples for large language models are GPT, BERT, T5, and so on. If you use ChatGPT now, it has a collection of different models. It uses large language models. It uses large media models like DAL-E, and also using some file processing. Okay. Now, another terminology which you will hear quite a lot is a foundation model. What's a foundation model? A foundation model is basically another terminology for a large language model. So transformer models were the architecture which we trained the model on, and then foundation models is the type of the model itself. So don't confuse these two terms, because this is just another way of calling large language model by calling them a foundation model. And the way of saying this is that a foundation model is a big toolbox, and a large language model is one of the tools inside that toolboxes. To give you an idea on how many foundation models are out there are quite a lot of foundation models out there, and the list is increasing every single day. And we know about ChatGPT because it came around, it was a bit later than, I mean, GPT-3 was announced somewhere around 2020, but we started using ChatGPT in 2022, somewhere around that time, end of 2022. But take a look before that. Take a look at all the models which were in 2018. There were even models being developed then. These were large, these were foundation models, big models with a huge amount of data, generative AI focused only on creating content. And you had OpenAI created like one in 2018. People didn't know about it. Then you have Google was creating BART, large language model, and so on and so on. Microsoft created their own. Facebook created their own. Hugging Face created their own in 2019. So, I mean, there are many companies creating their own generative AI models. It wasn't really a new thing. The only special thing with OpenAI was that they made it available to people like us who were not using AI on a daily basis, and they made it available through a chatbot. And that kind of changed the whole game. Then everything became more super important and super interesting for everyone. Huh?
It's probably outside the scope, but I was just wondering, since Google has so much access to data anywhere and everywhere, and they have this chatbot that they use for their phones. I'm not, I just don't understand why this relatively unknown company got ahead of Google doing this chatbot when Google has been trying to sell the tools with the chatbot for so many years. It might be outside this, but I'm just
No, it's a very good, it's a very good question to ask. I will try to answer that. So Google has been trying to fix this for a very long period of time. Just to repeat the question, why wasn't Google able to do this, and why was OpenAI able to do this? When you look at the quality of various large language models or foundation models, you would see that more or less the quality is the same. You have even certain models which were trained on a higher billion parameters than the other ones. So why was OpenAI able to do something which Google wasn't able to do? This comes back to the philosophy of how small you are and how easily you can implement those changes. When you are a new company, and this is something with my experience, that when you are a smaller company, when you are working with new ideas, you are taking a lot of risk. Now, the difference between Google and OpenAI was Google was trying to make an AI model which would integrate with its products and provide better services to people through Gmail, through its chatbot. But they were not making a chatbot, a general chatbot. They were making an assistant which would help with different things. We all have used them and we know they suck. What OpenAI did was they just made the whole assistant available directly to you, which kind of helped us in writing our emails better and this and that and blah, blah, blah. Now, Google never wanted to create a chatbot. No one thought of creating a chatbot because they were like, what kind of use will it give to the people? But OpenAI took the risk because they were a smaller company and they could take that risk. Google didn't even think about it because they were always focused on improving their products. OpenAI was like, let's give it directly to the users and see how much value it brings by. Let's take the same example and map it to companies working around site, inside Norway, for example. The more bigger the companies are, the bigger you become, it becomes harder for you to do innovation because you have multiple people coming in the value chain, making decisions. You have more processes coming in and bureaucracy stops things. The smaller you are, the easier for you to be agile, to make decisions and to put things into production. So I think that was the advantage OpenAI had. Now, the bigger OpenAI becomes, perhaps they will lose this culture of innovation. Who knows? But this is what I have observed, that the smaller you are, the easier it is for you to do things because you take risk. What's the maximum that can happen? You can go bankrupt. You'll start something new. Okay, we need to talk about two or three things more. Parameters. What really is a parameter? If you look at this image, you have 94 million parameters, you have 100 million parameters, and you have billions of parameters. And then GPT-3 from OpenAI was trained on 175 billion parameters. And then you have Switch C from Google, which was trained on 1.6 trillion parameters. So let's understand what a parameter is. So parameter is the amount of information you can give to the model to understand anything about the world. So the more parameters you have, the more information the model has. It's like the brain of a child as compared to brain of an adult. The brain of an adult will have more information because, yeah, certain time has passed and it has developed and gathered all the information. A child has not lived that long enough, doesn't have that much information. Therefore, brain of a child has less parameters as brain of an adult, simply put. So the more parameters a model has, the more context, so context is a wrong word, the more information it has to give a specific decision. Another thing which is used quite a lot in large language models is called token. You will hear this word a lot. And when you hear the word token, the word token, what it essentially means is that any word, any sentence, any punctuation which you use to train the model or do a prompting towards the model, that would be a token itself. A token does not necessarily have to be a word. It can be a sentence, it can be a punctuation, or it can also be a word. Now, a context window is how much information you're giving at any specific time to the model while asking a question to the model. For example, if you were using GPT-3, now we're using GPT-4, but if you were using GPT-3, the longest question you can ask GPT-3 should not exceed 2048 tokens. That can be words, that can be sentences, that can be punctuation, but if it's more than that, GPT-3 will not understand it. So that's the context window, how much you can ask the model at any given time. You need to know these terms because these are used widely when it comes to development of a large language model. We talk a lot about the context window, we talk a lot about the tokens, we talk a lot about the parameters, and then we talk about what kind of model you are creating. Any confusions over here? All right, cool. What I'm going to do now is I'm going to take you back to a real world example of Router GPT, and I'm going to tell you how Router GPT was made. Now you know the basics of generative AI, the basics of large language models. We will cover prompting in the second class, which will also be the last class of AI. But we will cover how to work with prompting, prompt engineering, and what prompt engineering really is. Then we'll be done with the introduction to AI class. And around that time, you will also get information about the final project. So give me 1 second. I'm going to stop sharing. Okay, so let's talk about how to create an LLM. a large language model. So there are two ways to create a large language model. One, the first thing you can do is to create a large language model from scratch. Now, when you start creating a large language model from scratch, you will get models like this. You will get models like ChatGPT. You will get models like Bard AI or Llama AI from Facebook or Meta. But they are extremely expensive to create. So you and I cannot really create them. A small and medium-sized company cannot create them. What we're talking about is millions of dollars of investment. You need to think about getting the right data in place. You need to think about getting the right infrastructure in place. You need specialized hardware to train the models. And then you're talking about X amount of months or years before you can release the model. It's very straightforward, but it's a lot of investment needed. And yeah, normal companies cannot really afford it. So one way of doing this is to start from scratch, or another way of doing this is use a process called fine tuning. Now, fine tuning is a process. What you do is you take an existing model as is, and then you retrain the model on your own specific data. That is called fine tuning. And if you do that, you get a model like Router GPT. So what we wanted to do was we wanted to create a model which would work for the transport sector inside Norway, all of the transport sector in Norway. And we were like, can we make one model for all of them? Obviously, we had to start from somewhere. So we started from our own special data, which is any transport data inside Router. And what we wanted to do was, okay, let's build on existing AIs instead of building something from scratch, because we don't have the money, we don't have the resources, we don't have the time to do this. So that's where we started. The first thing we did was to look at all existing large language models. So there are open source models and there are closed source models. And the closed source models are the commercial ones, which is GPT, Bard, and MyAI, which is based on OpenAI. But you have a lot of open source models also available in the market. So you have Llama, Open Llama, Falcon, Bloom, and so on. There are more coming every other day. And we did an evaluation. Now, being a Norwegian company, we have data which is in Norwegian language. So for us to create a large language model on a large language model, we could not use a large language model which was working in English language. We needed something which would understand Swedish language and Norwegian language. And when we tested ChatGPT, for example, GPT-4, we found out that it worked very well in English language, but it didn't work so well in Norwegian language. So there was a problem for us, like we needed something which could work in Norwegian language. So then we realized we now have two things to work with. We want our long-term goal is to have a model which will work for the transport sector data, but we also need a model which could understand Norwegian language. And we realized we need to fix the Norwegian language part first before we can fix the transport sector faster. So what we did was we evaluated various models which were available in the market. We realized Llama 2 from Facebook, which is an open source model, works very well for us. This model is already made as an open source on a lot of data by Facebook. They have tested in different parameters. And we are like, let's pick this model and fine tune on our own data. But we then realized that it doesn't really work. So that's the image for Llama 2. We then realized that Llama 2 doesn't really work that well in Norwegian language. So we were like, okay, let's retrain in Norwegian language. Now you need, for you to be able to train the large language model on Norwegian language, you need Norwegian language data. Now, fortunately, there's Språkbanken, the national bank. No, the national. What is Språkbanken in English? Sorry? Language Bank, thank you. The Language Bank of Norway is also associated with the National Library of Norway, and their eventual goal is to create and research on languages inside Norway. So what they did was they made a lot of data sets in Nynorsk, Bokmål, and other kind of dialects around Norway, and they have collected it and made it as open source available for all kind of research purposes. So we downloaded those data sets and we found the ones which worked for us, and we trained the model on those data sets. Our first plan was to have an LLM which works in Norwegian language. And then we started testing it internally. And this is the test we got. So we only spoke Norwegian with it, and the model started communicating Norwegian back. And when we were done with that one, we then came to a point we realized, okay, it works well. Norwegian language works well. We then started building applications on top of it. Now, a model itself can be an assistant for you, but it can have a lot of value for you if you start building applications for different companies or, yeah. The first thing we did was we have a lot of data from HR, human resources in the company. And there was a lot of information about things you can do, things you can't do, benefits you have, and so forth. So what we had like a chatbot. So when you talk to the chatbot kind of gives information on where to find different information. The problem with the chatbot was that every time you asked it a question, it always pointed you to a link, like go and we think the answer is over there. The way the chatbot was programmed was a rule-based thing. Like if a question comes on this, go to this one. Question this, that's the answer. When we use Router GPT, which works on the Norwegian language, and we created an application. So what we did was we took all the HR files and we fed the models all these files. This technique is called like grounding, I think. I'm not sure the word. Ground. Okay, yeah. So we just gave all the information, and what we did was we tested it out. So the same question we were asking the chatbot was pointing us to links. And when we were asking our Router GPT, it was actually going through those PDF files and giving us the right information back, which is a huge advancement because every time information changes, data changes, we had to go to that external company, ask them to update it. That wasted time, that involved some kind of cost to the external company and so forth. But now you had an assistant inside the company which was picking up every kind of updated information and also giving you updated information back. No hallucinations. So we kind of realized it works well for us. So what we did was we released Router GPT. We realized what we had created was something so useful that others in Norway can also use it. So we released Router GPT as open source. So this is one of the large language models which works in Norwegian language. And we put it on a community called Hugging Face. Hugging Face is like GitHub for different kind of projects, AI projects. And until now, it has been downloaded around 1,000 times. So there are 1,000 people or companies who are using this in doing various kind of large language tasks in Norwegian language. And we're also getting a lot of feedback from the community on how to improve it. Our plan right now is to further develop it into a transport model. Again, the fine-tuning approach. Now, it took us around 1 day to train the model on Norwegian data. So we had to run it continuously on specialized GPUs. And then we got the model right. Then we had to evaluate the model and see if it was working fine or not. And it took us 3 to 4 months to find the right kind of data to be able to feed the model. So again, data paths were extremely hard, and training the model on the data was faster, but still like it took us like a day to do that. Any questions? So yeah.
So it's just like a chatbot.
Yeah, it's a large language model, so you can connect it with a chatbot.
Okay, yeah.
But it can be an assistant, like you can connect it with email or anything.
It's not going to do anything right now. Like it's not going to do anything right now.
No.
It's like yourself.
No. The model which you will all get access to is not Router GPT. It's another model called Norsk GPT, which yeah, you will get access to that model, which also works in the Norwegian language, and you will have an API to ask different questions to it. I'll tell you how to communicate with that model and what kind of communication you should do, and then we'll do evaluation of how to evaluate the model and how to work with this model. All right. Thank you so much for today. And please, oh yeah, last question. I uploaded it's not a sample exam, but a structure of the exam of how it will come in the paper. So take a look at, go to Canvas and take a look at what kind of format you can expect the exam to be. It will be multiple choice questions.
So the project we just had, it was quite different for information relevant to what we were. There was so much information that sifting through it was hard to find what I should actually do. Is there like a for machine learning, supervised machine learning, which is what I thought it was like because I tried to read.
I need to talk to you. I can't hear you, but can we? Yeah. I'm gonna stop recording and exit Zoom. Thank you for today.